Hello, honors physics students. Please make sure you have your notes open and you've already printed out the notes page called Introduction to Electrostatics. Alright, so our next topic is electrostatics, and we're basically making a kind of a big break in the year. The year is broken into three major parts. The first part was mechanics. That was all stuff with motion and forces and energy and interactions among matter. And we took our sort of digression into waves and sound and light and optics, and now we're taking on our third major part of the year, electricity and magnetism. But as always, we like to sort of bridge the topics. So we'll start with a real simple question here. What produces light? We just finished our topic of optics, before that was light, and we've gone over this a number of times throughout the year. So just pause the video, see if you can remember what produces light. Okay, so of course you know that light comes from the sun. Well, it's happening inside the sun, so this should sound familiar. Of course, there are nuclear reactions happening inside any star, producing light and all those different types of electromagnetic radiation. But of course, we don't only get light from the sun, we get light from light bulbs, and so you might remember what's happening inside the filaments of a light bulb, or the flame of a fire, or the gas of a fluorescent light bulb. If you don't recall, if you want to look back when we first did with waves and sound, it was accelerating charged particles. And back then when we said this phrase, we said maybe you don't know what charged particles are, we'll come to it another day. Well, today is that day. Today we're going to start talking about charged particles, what it means to have charge. So let's make a chart here in our notes of charged particles versus some neutral particles. In class I would ask you what of these sort of particles you know, and I'm sure you've had some experience with some of these things. I'm not going to waste any time here. We know that of course the proton, that's a charged particle. By particle I mean some tiny little bit of matter. And of course electrons are charged particles. And usually along with these are associated neutrons, but of course neutrons are not charged, neutrons are neutral, hence the name, right? So they go on the neutral particle side. At this point I'd ask for any other particles you know, tiny little bits of matter, either that have an electric charge or don't have an electric charge. And you've seen some of these things before. Definitely we should have come across the atom, and by definition an atom is a neutral object. And then usually the answers from this point vary, so I'm just going to put a bunch of the ones that usually come up under the charged particles. We have ions and quarks. It's okay if you haven't heard of some of these things, we'll go over some of it. And then on neutral particles, some students have heard of things called neutrinos, which also of course is implied that neutral, it's got that neutral part of it, right? And then photons, that's the particle model of light. And since light doesn't even have matter to it, it certainly can't have an electric charge. But what is this charge? What does it mean to have charge? Well, one way to think about it is that some objects have charge, that's these over here. Some objects don't have charge, that's these over here. And the ones that have charge can interact with each other in some new way that we haven't seen yet before. So objects that have charge can interact with other objects with charge. Objects that don't have charge cannot interact with objects that have charge. So this is some new fundamental quality that some objects have and some don't. And if they have it, they can do things to other objects that have it. And if they don't, they can't. I know that's not a great definition, but that's really a very basic definition. That's something new, some new property we haven't encountered yet. There's going to be some new sort of interactions. But now is a good time to mention what charge isn't. And charge is not energy. And this is where a lot of students get confused, especially because when your cell phone dies and you plug it in, you say you're charging it up. Well, that's not really our physics definition. What's really happened is that your battery in the cell phone has lost energy. And when you plug it in, you are putting the energy back in. Batteries don't store charge, whatever that is. Batteries store energy, right? Now, so that means that when you're plugging your battery in, you should say you're re-energizing it, but I think people will probably give you a funny look if you say that. So you can still say you're recharging it, but you just have to understand that the way we use the word charge in physics is different from the way you use it in everyday life. In everyday life, charge and energy kind of mean the same thing, but in physics, they are two fundamentally different ideas. And so it's okay if you still don't quite know what charge is, but at least you should know it's not energy. As we encounter more and more examples of objects that have charge, you'll get a better sense of what it means to have charge. The symbol for charge, of course, is a lowercase q. Now, of course, that's not, it doesn't make a whole lot of sense. I think we just ran out of letters. If we had to use Q for something, I've heard some people try to justify it by saying it's a quantity of charge, but I don't buy that for a second. So it doesn't matter. We're going to use lowercase q, sometimes capital Q, to mean charge. Now, some of these particles on this list here are maybe unfamiliar to you. You don't quite know how they fit in. So let's do on the right-hand side here a chart, a hierarchy of matter, how it all fits together. So let's start with some large-scale objects. Things you can hold in your hand and feel and touch, like desks and pencils and buildings and cars and things like that. And if you were to break objects down, maybe the next level down would be molecules. Now, I know students who have taken chemistry know not everything makes a molecule. Some things make what we call formula units, but let's not worry about the difference between the two. So now we have molecules, which are little bits of objects. And if you take molecules apart, the next level down would be atoms. Now, at this point, we get to some really fundamental building blocks of matter. In fact, when the atom was first conceptualized, people thought that the atom was the tiniest bit of matter, and for thousands of years, they thought it was, and they finally found evidence for atoms. They said, we've discovered this tiniest bit of matter, and then some decades passed by, and they found there were actually things inside the atom. There was a substructure to the atom, and these are the particles that you're probably familiar with, the three particles, the protons, the neutrons, and the electrons. And so they said, now we've discovered the smallest bits of matter. Maybe these are the tiniest bits, the very fundamental building blocks of matter. And technology progressed, and they started smashing things together, and they realized there were actually things inside the protons and neutrons. When they smashed them together, things flew out, which they then called the quarks. But the universe doesn't really let quarks be by themselves, so these quarks came right back together to form protons or neutrons or some other fundamental particles that you probably never heard of, but these are the basic building blocks. And then they tried the same thing with electrons, started smashing them into things, and it turns out nothing came out. So there's nothing inside the electron. Electrons belong to a particle, category of particles called leptons. And so it seems like this is really the smallest bits of matter, quarks and leptons, that combinations of quarks and leptons come together to form all the particles that make up matter, then build up to the objects you're used to. Now, of course, we've been wrong before. We thought these were the tiniest bits of matter, and technology progressed. So maybe technology progressed and showed that quarks and leptons have some things inside, although there's a huge amount of evidence saying that's not true, that really quarks and leptons are the tiniest bits of matter. It doesn't get any smaller than that, but we've been wrong before. Okay, let's start to talk about the atom specifically. We'll be focusing on this a lot, and we've already talked about the fact that atoms are electrically neutral, which means they don't have an overall charge to them, so they can't interact with objects that do have charges. We've also now seen that atoms do have a substructure. There are things within the atom. But I did mention it was decades between the idea of the atom and then discovering the atom. Actually, sorry, it was thousands of years before they discovered even evidence for an atom. Why is that? Why is it so difficult to locate an atom? Well, hopefully you know, of course, atoms are really, 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 really tiny. They're ridiculously small. In fact, they're so small the human eye can't see them. They do not reflect visible light. The wavelengths of visible light, 400 to 700 nanometers, are just too large. They would pass atoms right by. And so you will never, ever see an atom. The human eye can't do it because the human eye needs light to bounce off the object and go into it, right? We've talked about that before. And so if you ever see a picture of an atom or a diagram of an atom, it's always some artist's conception of what they think an atom looks like, some sort of model they built up. Maybe they did use other tiny objects and bounce off the atom and then use the evidence to show what the structure of the atom looks like and how it, in general what it looks like, but they can't use light to do it, because visible light at least will not bounce off the atom. Okay, so now we have a sense of the structure of matter. We have a little bit of idea of what it means to have a charge. Let's go on to the notes page where we look at the structure of the atom in a little more detail. Now, there have been many, many scientists over the years who have come up with ways of modeling the atom. We're going to be focusing on what's called the Bohr Model, introduced in 1913 by Niels Bohr, and it's the one you're probably most familiar with. And so we'll start from the inside out. So, of course, you know the inside, the center part of the atom, which I draw here as a dashed circle, is called the nucleus. I draw it as a dashed circle because when it was first discovered, they thought the nucleus itself was a particle, and then very soon afterwards they found there were things inside the nucleus. I'm sure you know the things inside the nucleus are the protons and neutrons. Let's start with protons. So here I'll draw protons as circles with plus signs inside, because I'm sure you know that protons are positive. You've done over all this in a previous course. This is all very good review. Now I'm drawing the proton as a circle. That's not exactly true. Atoms, we just said, are so small the human eye can't see them, and these particles are inside the atom. So protons are so ridiculously small. We call them point particles. We pretend they only occupy a single point in space. We can't really draw that, right? So we have to draw something or other. So we usually draw it as a circle with a plus sign inside. And just to color coordinate, I'm going to draw them as red here. If you happen to have different colors, you can do that as well. But as I just mentioned, atoms are so small, visible light doesn't bounce off them, and protons are smaller than that. So certainly, visible light won't bounce off of them, and so you'll never see a proton. And so we can't say protons even have a color, because you will never see them, right? They don't have color. So I'm just going to draw them as red here because it's easy to distinguish among the other particles. So we'll draw them as these circles with plus signs inside. I'm putting 3 protons in the nucleus. There are also neutrons inside the nucleus, and so we're just going to put 4 of them inside. Here I'll draw them as black circles with zeros inside, indicating they have no electric charge. They are neutral particles. And again, these are smaller than atoms, so these are also point particles, taking up only a point in space, but we'll draw them as a circle with a 0 inside. What else is inside the atom? Of course, we need the electrons. Where are they? Well, you know they're outside the nucleus. So I'm going to draw this dashed line here, indicating the orbit of the electrons. I'm going to put a couple of electrons there, which we know are negatively charged. Electrons also are so small we call them point particles, and electrons are not blue. But I'm just using that so we can see it very easily here in the diagrams. If you want to color coordinate, great. How many electrons do we need? Well, you should know if there's 3 protons in the nucleus, we need 3 electrons in the atom to balance it out. So overall it is an electrically neutral object, as we mentioned before. But those of you taking chemistry may know that the first ring or orbit, or sometimes called energy level of electrons, can only hold 2, and so we need a second level to hold the third electron. So we draw a second shell here, as it's sometimes called, or energy level, and now we'll label these are the electrons. Now I'm drawing these as dashed lines because a lot of times in books or online you'll see them drawn as solid lines, and I think some students get a little confused and think there's an actual object there, an actual physical ring on which electrons sit, and that's not true. Also, I want to draw arrows here to show these electrons are in motion. That's something that's often also left off of the diagrams because you're seeing a static image very often, and you really want to be visualizing that while the protons and neutrons are sort of stuck inside the nucleus not moving, the electrons are in constant motion but are in this Bohr model shown here as circular orbits. It's not exactly true, but for this model it's good enough. And so really you want to be visualizing electrons are tracing out circles, and so this dashed line is like the path of the electrons. So they're moving so fast, it's almost as if there's a solid object there, but it's really just electrons zipping around so quickly that you can't really distinguish between the two ideas. Also, to be very aware, what we're looking at here is a 2-dimensional model. In reality, it should happen in 3 dimensions, and so sometimes we draw the cluster of particles in the nucleus sort of like this, sort of bunched together here, maybe like a bunch of grapes or something like that, and the electron orbits are all over the place, really in 3 dimensions. In class I'll be able to show that a little better, but here you want to try to visualize these are circles seen on edge, sort of in 3 dimensions, and of course this is also the picture that's on Jimmy Neutron's t-shirt. I'm not sure how much longer I have on that reference. For those of you who still remember the Nickelodeon show Jimmy Neutron, that's what he was looking at there, a 3-dimensional view of the Bohr model of the atom. Now, there have been plenty other models of the atom. The Bohr model is certainly not our most successful or most recent, but for our level, this is a good enough version for what it looks like, although we should recognize it's not really right. One more note about this is I might ask in class what chemical element we're looking at, and those who are taking chemistry will be able to tell me we're looking at lithium. Now we know it's lithium because there are 1, 2, 3 protons in the nucleus, and that's sort of a fundamental idea here, that the number of protons inside the nucleus of an atom defines which chemical element you're looking at. So anything that has 3 protons in the nucleus, regardless of anything else that's there, is lithium. It'll act as lithium, and anything else that has a different number of protons acts as something else. Now, if I take one of these electrons away, I've not changed how many protons are inside the nucleus, and so it's still lithium. It's just not a lithium atom. Here, it was a lithium atom because the number of protons, 1, 2, 3, matches the number of electrons, 1, 2, 3. They balance out for an overall neutral charge. But when I take one electron away, it now has an overall net charge. The protons are beating the electrons. It is now overall positive, and now is not a lithium atom anymore. Now it is a lithium ion. And that was something that I mentioned before in our chart of charged versus neutral particles. Ions are just atoms that have either gained or lost electrons, so now they have an overall net charge. So we can't define them as atoms anymore because by definition atoms are electrically neutral.